All right, so okay, so here is what I was talking about. So I've introduced you to the Knearest Neighbor network. There is a description of what KNN algorithm is in rather luxurious terms, and then there's the uppity description taken from Wikipedia, which is the source of all human knowledge. And what I just described on the board was this part of the algorithm. In KNN classification, the output is a class membership. Our two classes were red and blue. An object's classified by a plurality vote, which is the uppity way of saying count how many reds, count how many blues are in the green circle, and whichever there's more of, that's what the new value is assigned. And if you are silly enough to set the nearest neighbor value to 1, it is indeed the nearest neighbor. In regression, if we use it as a regressor, everything is the same except that last step. Instead of a plurality vote, the ones that are contained in the green circle are used to pass a regression line through the data, and then your result is that. And I have an example of that. And then you can read the rest on your own. A peculiarity is that it's somewhat sensitive to local structure of the data. We can kind of see that in the picture. Depending on the shape of those. Oh, who's sending me email now? There, I just believe I let either Vladimir Putin or Bill Gates have access to my computer. So the background of the KNN is rather straightforward to explain, and it's based largely on this conjecture called the first law of geography. I didn't even know geography had laws, but I guess they do. It says that everything's related to everything else, but things that are close by are more related than things that are distant, which kind of makes, it has some logical sense. Everybody in this room is related to one another by virtue of the fact we're either students, staff, or faculty at Texas Tech University. Now, it's quite possible that there are students, staff, and faculty in Costa Rica, for instance, because we have an operation there. But if you were to fly down to Costa Rica right now, pluck someone off the street, and they don't cut you to bits for doing that, the chances of that person having anything to do with Texas Tech are pretty slim. And it's because they're not here. The fact that we're here and close to one another kind of satisfies this first law of geography. That may not have been the best example in the history of the world, but it's okay. It's the last class of any consequence in this class, so everyone should be thrilled. So based on that first law, the KNN algorithm was created, and it's kind of oversold, but it's really pretty cool. It's not like they sat down and thought, oh, we need to invent a classification algorithm. Whoever did this in the first place did the obvious. It's like, well, I'm trying to find this thing, and they're either green or red, and so maybe whatever's closest makes the most sense. That's how it really came about. But let's go ahead and pretend that they sat down and thought really hard about it. The algorithm works fairly simply. It calculates the distance of a new data point to all other training data points. Now there's one of the flaws in it. It calls that a new data point. That new data point isn't really of any value until we ground truth it or verify it. So when Amazon decides that you're going to buy red socks instead of blue based on your search, so far so good, but But if you actually buy the blue socks, then there is something wrong with their algorithm, and that's the update phase, which actually we almost never talk about in this class and others. A proper algorithm would have a way to update information based on new ground truth. So once it's classified that, that's fine. We can do that. We can do that till we're blue in the face or red in the circle. But until we verify the new ones, they don't become part of the database. So we calculate the distance, and the distance can be any type, and we're going to look at a few different types of distances in the picture coming up. Then it selects the k nearest ones. K is a user-assigned value. How many do we think is appropriate? The 1 is the smallest value that k can have, and I guess the total database is the biggest value, and wants somewhere between the two. So when it's used as a classifier, it assigns to the data point the class to which the majority of the k points belong. When it's used as a predictor, it assigns to the data point some mean prediction value based on the associated values of the k data points. So you can think of it as taking those k data points, passing a regression line through them, and then making the prediction on the regression line. An example of KNN as a predictor, we'll go take that because I think it appears again later. Yeah, it does. Nope, we're going to go. Okay, it does appear there later. Okay, good. We'll go take the exploration later. It's shown by solids and rivers. You recall the solids and rivers, that was on your exam for those of you that actually took it and still remember that. You were asked to do something different with that particular database. So let's look at the concept of distance in multidimensional space. So the distance that I drew up on the board is this one. It's called Euclidean distance, and it's the distance between, it says, two real valued vectors, although there's other possible choices. Most distances are measured using Euclidean norms. Another one is the L1 or the Manhattan distance, affectionately called taxicab distance, or I guess it would be called Uber distance now, or city block distance. And that is a measurement that takes into account that it may not be physically possible to go from the red dot to the blue dot in the plane that the data are lying in. So if you're in New York, with current taxicab Uber technology, current as of today, you have to follow the directions of the streets. You may have, you can't go on the most direct route as indicated by Euclidean distance. And so the actual distance you have to travel is called the Manhattan distance. If you're in the world of helicopters and have the kind of money to fly from building top to building top, all bets are off. You probably don't even need to know anything at that point. Another type of distance is called Minkowski, and the Minkowski distance is essentially, it's this equation, except instead of being a square root, it's a pth root, and everything is raised to the p power. So if you can choose letters of the alphabet wisely, you can get something named after yourself. So this dude Minkowski, who grew up in Manhattan and made pastrami sandwiches as a kid, came up with this distance measurement. So if p equals 1, we have Manhattan distance. If p equals 2, we get Euclidean distance. If p equals 0, we get completely useless results. Then there was a Russian dude named Chebyshev, and perhaps you've heard of him before because he was very unequal. He had inequalities named after him. It's the first one that noticed that Stalin was more equal than everyone else. He was purged for that. And in Chebyshev distance, it's the longer of either the horizontal or, in this case, the vertical distance. So think of it as a taxicab distance, but it's the longest street that you have to take to get from point A to point B. And then there's a few other ones. There's a cosine, and there's one named after Hamming, who used to work in the same delicatessen that Minkowski did. He made ham and cheese sandwiches and was very interested in character strings. I'm making a lot of this up. I'm sorry, that's hard for y'all to translate. But by far, probably the three most common, well actually let's simplify it. The most common is a Minkowski distance with P set to either 1 or 2. Let's go look at an example of K-nearest neighbor used as a regression technique. So if you remember on your exam, you were introduced to the Solids and Rivers database. Let's see if I can get one. Oh, it's going to download it. Hopefully it got here, and hopefully the file will open. Okay, so you perhaps remember that file. Maybe you even looked at it when you downloaded it and opened it in Pandas and did the header run on it, and you got the first 5 lines. So it's a database of flow rates and solids transport in rivers. It's got 13,000 some odd rows, so it would be kind of a pain in the neck to work through it in Excel, although I suppose you could if you were insane enough. It turns out that as a practical matter, there are a handful of columns in that database that can be used to estimate solids flux. And so the ones that were hit upon by researchers, see which researchers was it? The researchers that did this report, because this is where this database came from, is the slope of the river, some measure of the mean grain diameter, a value for discharge, a value for section velocity, which is stupid because these two are highly correlated, a value for the exponent, so the value of P in computing distances, and then how many neighbors we want to count. Hopefully I can go from memory and get values that are in the database and not too far outside the scope. See, those are in meters. So I'm just entering numbers because I have prior knowledge of what the database should contain in it. Now is the distance thing. Let's go ahead and just do Euclidean distance, and I'll take let's do the 9 nearest neighbors, and when I press submit query, it's going to go into the server. It's going to run a Python script that's going to calculate all the distances of the 18,000 things in the database, sort them into increasing size, count through the 9 that have complete entries, and use those to produce an estimate of the solids flux. Hopefully it actually works. There, it's all done, and it did that right before our very eyes. So it estimates the average solids flux as 0.0003152 kilograms per meter per second, or the concentration in that flow of 0.02 parts per 100,000, which is a common value, a common unit for solids concentration. Then it draws a picture, and it says bar plots of the 5 nearest neighbor values, input values, and estimates based on all the search neighbors. So on the left panels, the gold bar is the input value, and then the blue bars are the values of the 5 nearest neighbors. We see that our slope is at least within the range of observations. Our diameter also is, our discharge value is a wee bit low, and our velocity is a wee bit high. And in the right one, the purple bar is the estimate. So you can think of that purple bar is the average of the 5 blue bars to its left. for solids flux and solids concentration. So these lower values certainly influence the choice of purple bar. If we had chosen n equals 1, it won't redraw the picture, so there's no point, but n equals 1 is probably this tallest bar, so it would tend to over-report what the solids concentration is in this particular database. That's an example of Nearest Neighbor, and we could go look at the code, but it's pretty ugly, and we will return to our class. So hidden in that are some other tricks. The first one is that in the Nearest Neighbor approach, the scale of the predictors influences the outcome. So if one of these axes, let's suppose that the value goes from 0 to bazillions on one axis, the other one goes from 0 to 3 on the other axis. And so if we were to plot that, that would look almost like a horizontal line of blue dots and red dots. It'd be very difficult to tell in the vertical axis what effect it has if we stay in native units. And so what's done in that is something called data normalization. And essentially we rescale the predictor axes so that each one has roughly the same weight when it contributes to the overall regression or classification. So reading it in words, if the values of one predictor are several orders of magnitude larger in the database than another predictor, the two can't be directly compared when computing a distance, because the big value will always clobber everything else. In such a case, one way to do direct interpretation is to use normalization. Normalization serves the purpose of bringing the indicators to the same unit scale or unit base and makes distance computations appropriate. Normalizing is done by a variety of standardization techniques. The two we'll look at here are z-score standardization and unit interval. So the z-score standardization goes to the database or the collection of reds and blues, and in any one of the prediction axes, it computes the mean value in the database of those things, the variance in the database of those things, and then transforms the actual x value to its z-score relative to the mean. So the values of the z-score will go from minus infinity to infinity, but from a practical matter, about minus 3 to 3. So it's measuring how far away from the mean value you are in that axis. And it does that for all the other axes. So there'll be a z-score for each axis in the prediction field. And then when it's done, we calculate distances in z-score space, do our classification, and then if we're going to actually do regression, we would convert back to original space. If we're just doing classification, we're done. Another one is 0-1 standardization. You can read this faster than I can read it to you. It has the same goal. It's trying to rescale the predictor space so that they're all comparable, and it takes the smallest thing, assigns it to 0, biggest thing assigns it to 1, and works from there. The main critique of 0-1 standardization is that generally we're using these tools to do what is the equivalent of extrapolation. We're trying to figure out values that may fall way to the right or way high in our drawing. With 0-1 standardization, we can't extrapolate, because if we go beyond the range of observed values, the algorithm has no way to proceed. So because of that, the 0-1 extrapolation is often not used because it's somewhat useless. Just defined useless, not used. If you were assured that your predictor field collection contains the highest and the lowest possible value, then 0-1 would be just fine. But if you don't know that in advance, it's not the preferred choice. So let's look at a quick visual example. This example is literally no different than what I drew on the board. Let's suppose we have a data set with two variables, which when plotted look like the following figure. So we have blue dots and red dots. And let's also further suppose that it's all nicely divided like this. And we now want to classify a new data point and determine whether it's blue or red. If you recall from logistic regression, we could have used that also, but what we would get is the probability of blueness out of logistic regression. And so if redness was assigned probability 1 and our value gave a probability of redness of 0.51, so 51% likelihood of redness, we'd have a hard time making the decision to classify it. Whereas with nearest neighbor, that question never gets entered. So let's suppose our new variable x is located right here at position, looks like 45, 50. We then calculate distances to all members of the database, and we're going to choose the 3 nearest ones. And so essentially, it's drawing an increasingly big circle until it just picks up the 3 things. So in this particular case, we have 1 blue and 2 reds. And so then the final step is to declare x will be declared red because 2 of the 3 nearest neighbors are red. And then here's a nice animation that was downloaded from the mighty internet, so it must be right, that shows that going on. So there's our unknown point, which is currently a black dot. It finds the 3 nearest ones. It says 2 of them are red, and it declares it red, and then it moves on. So that part of nearest neighbor is pretty simple. The hard part, which is not discussed either here or on the internet blogs that I read, is how to keep track of whether that point that you just made red has been verified to be red or not. That's what those verified customers on the Amazon websites when you're buying your widgets says. This is the greatest widget I've ever had since the last one I had. If it's a verified customer, all Amazon is telling you is that, yeah, we did sell that product to that username. So it still doesn't mean that the review is worth a crap. So why is Knearest Network even mentioned? Well, first, it's easy to implement. It doesn't require much training as far as an algorithm is concerned, and it's actually a pretty effective algorithm. For many instances, it's as good as something more sophisticated. And then here's a nice GIF of showing what KNN be like. It says, show me your friends and I'll tell you who you are. So if you remember nothing else of classification, remember Whoopi Goldberg telling you that she can tell you who you are by just knowing who you hang out with. There might be some element of truth to that. It probably wouldn't work for me because I hang out with some really weird people. I'll be okay if the revolution comes, if I can get to the right group of weird people in time. So let's revisit our iris database. Remember that? Mateo's grinning, so he remembers that, or he just got my one-liner. So in the iris database, we had 3 different kinds of flowers. We had setosa, versicolor, and virginica. And we were able to associate the length of a petal, the width of the petal, the length of a sepal, and the width of a sepal, which is, I guess, a different plant part. You got to know your plant parts to do this stuff. And this particular data set is well known and a classic data set in pattern recognition. So let's look at KNN to do that. Recall when we did flower recognition with this same database using logistic regression. Do you remember one step we had to make? Because in the logistic regression, we couldn't break it into 3 categories. So we chose to throw one out and then just analyze what remained. Well, with KNN, we don't have that requirement. And there would have been a workaround in logistic regression if we wanted to identify 3. Instead of throwing it out, you identify 2 of the same, one that's different, and if it becomes a one that's different, then you reanalyze that, so you just have a second step. So we're going to look at the database and see if we can tell what kind of flower it is based on these 2 measurements. And so let's just go through, see how simple KNN is. In this case, it's extra simple because we're going to use the sklearn package, which has the algorithm built in for us. If you were writing your own, there'd be a little bit additional complication because you would have to process the pandas database and do the encoding yourself. But from that point forward, it'd be pretty simple. So, as we usually do, we load in every library on the planet, including some that have not been invented yet. In this case, we use NumPy, pandas, in case we come across a bear. Plotting library, we need the sklearn library. We use Seaborn so that we can do cool plots. And then we will issue the magic directive matplot inline, which allows the plots to appear in line with our notebook. This last one, this is a Jupyter kind of thing. It's not required for it to actually work, but it is required if we want to see the plots. And we will now read the remote directory. I'll show you an even newer way to do it. We can take the URL. The names assignment is done ahead of time. And here's what's pretty cool. In the pandas package, you can read a file simply by putting the URL as the first argument. So that internally it's doing what we've done so far already. It's getting requests, it's building the request, it's downloading the file, verifying it, and then saving it locally. So let's go ahead and run that. Yay! And we will look at the head of the data set. Sometimes I do tails. A 50% chance of heads or tails. So there's our data set. It's no different than last time. If we run our describe function, we get the same kind of information. But now we will split the predictors and the target. Our target value is this class column. So sepal length is column 0, column 1, column 2, column 3. Column 4 is our class. So we're going to declare capx, which is the data set subset where we pull the values starting from column 0, ending at the last column -1. So we're going 0. Instead of colon, comma, colon -1, we could have just put 0 to 3. And this last one is all the values, including the 4th column. So we'll go ahead and make those splits. Now we're going to want to build our training and our testing subset. And like before, we did logistic regression, is we want to reserve some of the original database to test whatever our classification model is, so that we can generate confusion and get some feel of the quality of the classifier to actually classify our information. And here it looks like we're set up for an 80-20 split. So we're declaring the test size, 20% of the whole thing, and the internal package handles the 153 things, bringing out the 20% of that. It's roughly about 30. So here, if there's 150 records, it will use 120 of them at random to train the classifier, and it will reserve 30 of them at random to test the classifier. And an ideal classifier would be in the test set we get perfect fit. And because it's random, we might get it this time. And then to actually run the KNN classifier, it's really pretty simple. We're going to use the sklearn package. We're going to use Knearest classifier. We're going to tell it how many neighbors, the K value, and then we tell it the training set of predictors, and then the training set of responses, whether they're blue or red dots, and let it rip. And then the final set will be to produce predictions. So we'll produce something called a Y prediction, which will be, we run the classifier that we've just created, we run the predict function, and we feed it X test. So now let's go ahead and see how, we're done. We've just classified it. Now let's see how well it fits. So we can go ahead and get our classification report, and we have 2 of the 30 were misclassified, which is roughly 94% accurate, which is not bad. And we'll go ahead and we'll plot the confusion matrix. And so when the actual labels 0, our classifier predicted 0 7 out of 7 times. When the actual label was a 1, our classifier predicted it as a 1 10 out of 11 times, so 1 failure here. And when the actual was a 2, our classifier predicted it 11 out of 12 times, and then there's the 1 failure right there. That's not a bad classifier. As long as that's not life or death of you or your company, you probably go with that. If you were in Amazon, you can afford 1 in 11 failures because you can go ahead and, since you already have the credit card information, just take your money anyway. What happens if we use a different value of K? So we can kind of answer that manually. Let's suppose more must be good, right? It's Texas. So let's suppose we do 15 classifiers. Not much change on our, no change in our heat map, and no change in our, oh, that's because I didn't my bad, I didn't reset the test set. Let's go ahead and run the randomizer again. Pretty much the same accuracy or precision metrics. The map is going to visually look the same, although there's some different numbers here. So we got a 2 here. So going from 5 to 15 neighbors didn't seem to make, it made a difference, but not much of one. And rather than do that by hand, let's go ahead and have our computer do it for us. And so what we'll do is we'll have it go ahead and repeat classify using 1, 2, 3, all the way up to 50 nearest neighbors. We will pull a mean prediction error from that, and then we will make a plot of error versus neighborhood size. And if I could make it sing, I would have it sing, "Who are the people in your neighborhood?" So what this plot is showing is the prediction error as a function of neighborhood size. So we start with a neighborhood of size 1 and work our way up to 50. And so here we see 1, 2, 3, and 4 have an error of a bit above 0.065. When we introduce that 5th neighbor, it's always that odd one. The error goes up to 0.1. Same for 6th and 7th. When we get an 8th, it actually error drops back down again. And if we had a big enough data set, these kind of plot something like a U shape. They'll tend to have a U shape, and you would use the bottom of the U to select the neighborhood count. Conventionally, if you don't have any idea whatsoever, I believe the default that's almost always chosen is 5, which is why it was in the solids and rivers case as an example. Okay, some final remarks. So what you'll do in lab is essentially you're going to repeat all this. Literally, you'll repeat all of it. And then you're asked to go ahead and use your classifier to classify a new value. So you notice that is not shown how to do here, but there are some guidance in the lab on what you need to think of. And if you want to learn more about classification, there's a lot of reading material documented here. If you can't read but you like to watch videos, you can watch these various YouTube videos. And it's definitely a different world because you were just told by a professor it's okay to watch YouTube videos to learn stuff. Probably one of the best training tools that we built as a collective society. But you have to be critical of what you're watching because there's a lot of garbage out there too. And there will be another 1 hour piece of garbage uploaded soon. All right, that's all I have for today on classification. You can learn a lot more from the reading than from me telling you. Just returning, all nearest neighbor classification is doing is it's finding distances from an unknown value to existing values in a database, and then ranking those within a certain search distance that you prescribe by how many things there are, and using that to decide what classification to assign to the unknown value. Okay, that is all I have for today. Are there any questions before you all pack up and leave? Okay, don't leave yet. I'm not sure if we should record your questions or not. I think I will. No, actually, it's project related, so I'll leave the recorder running. So what did you all want to?
No, we want to show you what we've done so far, so we can know if you're doing the right thing or not.
You want to share it with everybody or no? We could go look at the YouTube. Yeah, get it on your guitar. Let's see if anybody has watched any of the recent stuff.
I watched 2 of the classes that I missed. Got 2 videos.
And these are probably the only 2.
Open also the projects.
This is
No.
the description.
Yeah.
Hopefully the settings know it's.
This.
Yes, and
It doesn't know it's me.
also right.
But this one knows it's me. There we go. Okay, let's run our analytics. Actually, those are pretty good view counts. Lesson 22, which was Thursday, 3 people watched it, and the lab, 7 people.
Okay, so first question, what do we do with this? Like, what is...
Okay, so the question for those of you watching the YouTube is what is the strength equals B0 plus B1 times blast slag plus B2, blah, 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 blah. And then, so you need to come up with values for B0, B1,
And we did
B2.
that. So,
Okay.
like, we have this part,
I don't know
but, like, the log
part.
and...
Okay, so what you're going to do with the log is you're now looking at does a logarithmic transformation produce a better prediction than doing it in arithmetic space?
And then, like, how would we determine which prediction is better?
That's your problem.
Okay.
You have R-squareds, and you have other metrics that you can
Okay.
use. And it looks like, let's see, strength. I forgot what that third line is. Was that in my part? Oh, that's a power law version of the third model. So you have linear, linear of the logarithms, or the logarithms of the linear, and then power law.
Okay.
And then from those three, choose one that you like best.
Okay.
And that is literally the exercise.
Okay. I think
Yeah,
that was like
because-
the same thing as what? What was the other question we had? What was that?
And to know, like, what's the difference between what was it? No, what's it? There were two parts for it. Oh yeah, this part.
Actually, let me
So one is asking for possible data model structures, and the other data model fitting tools. The fitting tools are like the linear regression model.
Yeah.
Okay, so yeah, we did that.
So did we, like, out of these three options, like the log and then the exponent ones, could we have done like different models? Like, could we have done 3 different models and like analyze those? Or like,
Yes.
it have to be those 3? Okay, we did that.
The
I
issue
think we did
is the
hard.
ones I picked for you are ones that you can attack with linear regression.
Okay.
Okay.
Yeah,
If
because
Yeah,
we
'cause-
did.
Go to fully nonlinear, you get
Yeah,
kind of.
this ones where they use
Yeah, those look about typical.
Okay, sweet.
Let me show for the video audience what we're talking about. So it is in projects, and you are doing concrete, right?
Yes.
You get the one that does not have the answers.
You could do that one if you want.
Subtle. Okay, so here's what we were showing. The questions were related to what's going on here. That is 3 different models of strength. The first one is a linear model. So it says its strength is some intercept plus B1 times blast slag plus B2 times fly ash and so on. The next one is the natural log or the base 10 log, your choice, doesn't make a difference, of that same predictor tool. And that sometimes logarithmic plotting stuff straightens lines out. It doesn't actually straighten, they look straighter.
Okay.
And then this last one is beta 0 times the blast slag raised to some power, fly ash raised to a different power. It's supposed to be coarse raised to some other power. That's a power law model.
Okay.
And those, there are 4 categories of models that can all be attacked with linear regression. Those are 3 of the 4.
Okay.
Oh, okay. So I think we just did.
So, for example, with the strength, if you take the either base 10 or base E log of strength, you get log beta 0 plus E1 log of blast plus E2 log of fly ash, and then you can linear regress that to get the E1, E2, and so forth.
Okay.
So we log the values to find the the betas for the log one, because we did the linear regression model. I think this is the first type that this one, the regular one with B0, B1, and all this stuff. That's the one we did here. So then we would just get these values and log them and do the same thing and plot it again.
Yeah, if you logged the x-axis, what effect would that have? You have stuff going from 0 to 60, so it would squish it down. It wouldn't be very useful in this case. If you did the vertical axis, you're going from 0 to 60, you might go ahead and do it. You might find out that logarithmic transformation isn't terribly useful in this instance. But you still need to do the power law model because I see a little curvature in that, and power law might fit a little bit better.
Okay.
And it's real data, so I mean, the fact that your blue line doesn't, your red line doesn't nicely lay down and the blue dots don't all sit on it is to be expected.
Okay.
We could have given you a toy problem where everything is perfect, but then you learn nothing. You believe that that's what it's supposed to look like, and you beat your head years later, wondering why it doesn't fit.
Sweet.
So that is all that is asked for that. Let me see, I can show, since we do have one, I can't record it, so I guess there's no point of showing the plots. All right, we will start lab at the usual time. Oh, I need to, since you did drag yourself here, Jasmine, let's at least give you. I'm done. You're free to go. We'll have lab at the usual time. Have a good Thanksgiving, everybody. Okay. Shut down the recorder.